Hello and welcome to this lesson on chemical yield with specification reference 3.1.2.5. Let's discover what we're going to do in this video lesson. And we've just got one learning objective today. We want to be able to calculate percentage yields from balanced equations. And let's just at this point highlight that a percentage yield takes into account two different things. It takes into account an actual yield, and it takes into account a theoretical yield. And it's just a percentage of one over the other. Okay, so let's start off thinking about the theoretical yield. And here we have a statement saying what theoretical yield is. So it is the mass of the product that should be formed in a chemical reaction. So you're going to have a balanced equation, and it's the maximum amount that of product that you're going to get given the amount of reactant that you start with. Okay, and here is how we do it. So we're going to start off working out how many moles of the reactant you have. You're likely to be given the number of grams, and you're going to work out how many moles of the reactant you have. After that, you're going to refer to the balanced equation and work out how many moles of product you would expect given the number of moles of reactant that you're starting with. Once you've got that, then you can calculate the mass of that many moles of product. Okay, just using the usual moles equals mass over AR or MR, then you can calculate the mass from moles of product. And that's going to be the theoretical yield. That's going to be the theoretical yield. So a three-step process. And before we go on to working percentage yields, let's just give ourselves a chance to work through a real example to work out a theoretical yield. And here we have it. So let's read the question carefully first. So we're given the grams of iron filings, which is one of the reactants. So 1.40 grams of iron filings react with ammonia and sulfuric acid to make hydrated ammonium iron sulfate. Hydrated ammonium iron sulfate. That's our product that we're interested in. And the balanced equation is given to us. So you've got iron plus 1 mole of iron plus 2 moles of ammonia plus 2 moles of sulfuric acid plus in fact 6 moles of water give us 1 mole of hydrated ammonium iron sulfate plus a bit of hydrogen. And we're to calculate the theoretical yield of this reaction. Okay, so before we start, let's remind ourselves of our three-step process. There we are. And so step number one, work out how many moles of reactant you have. Okay, so the important reactant is iron, and we're given the number of grams of iron. So the first thing we're going to do is work out in blue, we're going to work out the moles of iron. And you'll remember that moles equals mass over, in this case, AR, because it's an element, the relative atomic mass. And our mass is given in the question as 1.4 grams. And our AR we get off the periodic table, and we find that that is 55.8. So that works out at 0.0251 moles of iron. So that's how many moles of iron we're starting with. Step number one done. So now we're going to refer back to this balanced equation, and in particular the molar ratios that are involved. And you're going to see that for every 1 mole of iron, we get 1 mole of hydrated ammonium iron sulfate. All right, so that means that the number of moles of hydrated ammonium iron sulfate, I'm just wondering how I'm going to write that down without taking all day. So let's hydrated ammonium iron sulfate. So the moles of those is the same as the moles of iron, which is 0.0251. So that is step number 2 done. And so now we want to calculate the mass of this many moles of hydrated ammonium iron sulfate. So the mass of anything is going to be the moles times the MR of this, in this case, because we're dealing with a compound. And we're talking about the mass of ammonium iron sulfate and it's hydrated. Okay, so with the mass of that is the moles of that times the MR of it as well. And the moles we've just worked out at 0.0251, and the MR, why don't we just switch colours and do it over here. So the MR of our NH4 iron sulfate is going to take some working out. So I'm going to use more space here because we've got quite a long sum. So first of all, the ammonium, nitrogen is 14, and we've got 4 hydrogens, so 4 times 1 is 4, and we have 2 of those. Okay, so that's the ammonium's taken care of. We have 1 iron. We already know iron is 55.8, and we have 2 sulfates. So 2 times sulfur is 32.1. Oxygen is 16. So 4 times 16, 64. That should be a plus. And then we've got 6 waters. So oxygen 16, hydrogen's 2, so that's 18, 6 times 18. Okay, and so if we were to work through that sum, we're going to get an MR of 392. So the MR is 392. So then our theoretical yield, switching back to blue, we can write in our 392. So our mass in grams is going to be 9.84 grams. 9.84 grams. And so the mass of the product in grams is our theoretical yield. And just to make that quite clear, let's write it out in full. Theoretical yield equals 9.84 grams. Done. So that's theoretical yield, but you'll remember from the learning objective we've got to work out percentage yield. So in order to work out percentage yield, we first have to think about actual yield, because you'll remember that percentage yield is actual yield over theoretical yield. And so here we've got a diagram of someone filtering some solution. Okay, and the point of this diagram is to illustrate that not all of the product that you make actually ends up being usable. So there's 3 main areas where product is lost. So actually usable product It's going to, so some of them, like little few drips you might leave in your beaker. Okay, so we might leave left in apparatus. Second one might be that the reaction is incomplete. And the third main one would be that you might get side reactions. You might get side reactions producing products that you don't want. Okay, so left in the apparatus we've got left in the beaker. Obviously some, if it's the solid you're interested in, some of the solids can be left on the filter paper. So left in apparatus is a common one. Not all reactions go to completion, so you might not get all of the product because of that reason, and also you might get different products that you don't want. Okay, so they're the main three reasons why actual yield is lower than theoretical yield. And there is the equation for percentage yield. So it takes account of both the product that you actually get after you've left some in your filter paper, for example, and it also takes account of what you should have got if everything went perfectly, which of course it never does. Okay, so 1 over the other times 100, it gives you your percentage yield. And that's an interesting number, especially for industrial companies making valuable products that they're going to sell. Clearly they want the percentage yield to be as high as possible because then there's less waste and more profit. Okay, so shall we have a go at one of these calculations? So here we have an example calculation where we need to calculate a percentage yield, and we're doing an experiment, and we've got 5.00 grams of copper, and we're heating that in air, i.e. oxygen, to produce copper oxide. Okay, so quite a simple experiment. You've got some copper, you're heating it in air, you're making copper oxide, and the theoretical yield of this reaction, right, so once you've taken account of your balanced equation, gone through the process we've just gone through on the slide before last, you work out that the theoretical yield for this reaction is 6.26 grams. But when the copper oxide was weighed, it was found to have a mass of 5.23 grams. And now we need to calculate the percentage yield of that reaction. Okay, let's do it. So we're just going to write out our generic equation first. Percentage yield is going to be our actual yield in grams, divided by our theoretical yield, also in grams, times 100. And in this case, our actual yield was 5.23 grams. Our theoretical yield, given also in the equation, 6.26 grams. Times 100 would give us our answer, and plugging that into the equation gives us 83.5%. Simple as that. Okay, let's have a look at another example. So here we have an example. We've got 0.475 grams of bromomethane, and that's reacting with excess sodium hydroxide in the following reaction. We've been given the balanced equation, and it reads 1 mole of bromomethane reacts with 1 mole of sodium hydroxide to give us 1 mole of methanol and a mole of sodium bromide. There we go, and we're given some data. We're told that 0.153 grams of methanol is produced. What is the percentage yield? Okay, so let's just get a head around what we've being asked for and what we're given. You remember that percentage yield, expressed as a percentage obviously, is the actual yield over the theoretical yield times 100, make it into percentage. But so both of these are in grams. That's in grams and that's in grams to give a percentage. Okay, so what have we been given? Well, when it's asking us for the percentage yield of what? Well, clearly it's of methanol, and we are actually given the fact that we have got 0.153 grams of it. So that, you can see, is going to be your actual yield. So you've been given the actual yield, but have you been given the theoretical yield? You've not been given the theoretical yield of methanol. What you have been given is the amount of grams of the reactant that you started with. So you started with bromomethane, and you're given a certain number of grams of that, and that's what you're going to make your methanol with. Okay, so what you're going to have to do is you're going to have to find out your theoretical yield, and it's the maximum amount of methanol that you're going to get from 0.475 grams of bromomethanol. So the first thing we need to do is to work out how many moles of bromomethane that we have. So moles of CH3Br is going to be the mass divided by the MR, and the mass is 0.475, and the MR, let's do it over here in red. So we've got CH3Br, carbon is 12, 3 hydrogens is 3, and bromine, just looking at a periodic table, bromine is 79.9. Add those three together, we get 94.9. So that's our MR. Switch back to blue, and we can put 94.9 back in here, and that will give us moles of bromomethane, which comes out at, and we want to give the answer to 3 significant figures, so that's 0.00501. 0.00501 moles of bromomethane. Okay, so now what we're going to do is we're going to look at the balanced equation, and so then we can see that for every 1 mole of bromomethane that we would use, we would get 1 mole of methanol. In which case, if we're not starting with 1 mole, but we are starting with 0.00501 moles of bromomethane, you will get the same number of moles of methanol. Okay, so we can write that down. Moles of methanol, which is what we're interested in, that's what we're calculating the percentage yield of, is the same as the moles of CH3Br, which happens to be 0.00501. So now we have the moles of the product, but as you can see from the equation, right, we need the grams. Theoretical yield, it's all about grams. So let's say the next line is going to be calculating the mass of methanol, and using a rearrangement of the same equation that we've just used, mass is moles times MR. Okay, so but it's MR of methanol this time. So we're going to use the moles of methanol, which is 0.00501, times, and let's switch to red again and write out the equation of methanol, CH3 OH. So again, that's 12, that's 3, that's 16, and that's 1. And that comes to 32. So let's write our 32 in here. And that's going to work out at 0.160 grams. Okay, so we had our actual yield from the question. We've now worked out our theoretical yield. So we have the two components of percentage yield. So let's just work out what the actual number is. Percentage yield of methanol, equals actual yield given in the question divided by our theoretical yield, which we worked out, times 100 equals 95.5%. So pretty efficient. And there you have it. And that's as far as percentage yield goes. I think you have it now. So that brings us to the end of this video lesson. Let's just make sure that we've covered off our learning objective, and it was to be able to calculate percentage yields from balanced equations. And we've done 3 or 4 examples to make sure we can do that. So I think we can give ourselves a tick here and be happy enough to move on. But if there's anything that you don't get there, then make sure you follow it up. Thanks very much. See you in the next video lesson.